The telescope that wasn't supposed to see this. When the James Webb Space Telescope launched, scientists had expectations. They expected clearer images. They expected better data. They expected refinement. What they did not expect was to be challenged, because within months, James Webb began seeing things that didn't just improve old theories, they broke them. Galaxies that looked too old to exist so early, atmospheres that shouldn't survive, chemical signatures that forced scientists to rethink how planets form and even how life might arise. This telescope wasn't just observing the universe, it was questioning it. So what exactly did James Webb see that shocked scientists? And why do these discoveries matter far beyond astronomy? To answer that, we must go back to the very beginning of time. Galaxies that shouldn't exist. According to our best models, the early universe was simple. After the Big Bang, matter slowly cooled. Gravity gradually pulled gas together. Galaxies were supposed to form slowly, small, dim, messy. But James Webb saw something else. The Webb shock. When Webb looked deep into space, it looked back in time over 13 billion years, and what it found stunned astronomers. Massive, structured galaxies existing just 300 to 500 million years after the Big Bang. That's not enough time for galaxies that big to form. Yet there they were, bright, ordered, mature. Why this is a problem? Current cosmology says early galaxies should be small, star formation should be slow, heavy elements should be rare, but Webb saw galaxies that looked too massive, too bright, too chemically evolved. Some scientists quietly asked, are our timelines wrong? Others asked something bigger. Is our understanding of galaxy formation incomplete? Not one, but many. This wasn't a single anomaly. Webb found dozens of these galaxies across different regions of space, which ruled out coincidence. These weren't flukes, they were data. Possible explanations and why none are comfortable. Scientists proposed several ideas. 1. Stars formed much faster than expected. 2. Early black holes accelerated growth. 3. Physics behaved differently in the early universe. Each explanation creates new problems because fixing one equation breaks another. Webb forced scientists to admit something rare. We don't fully understand how the first galaxies formed. And that's just the beginning. In the next part, James Webb uncovers something even more shocking: planets whose atmospheres should not exist at all. Impossible planet atmospheres. Before James Webb, scientists believed they understood exoplanet atmospheres. Hot planets lose gases quickly. Small planets can't hold thick atmospheres, and complex chemistry requires time. James Webb ignored those rules. A telescope that can smell worlds. The James Webb Space Telescope doesn't just see light, it reads chemistry. When a planet passes in front of its star, starlight filters through its atmosphere. Each molecule leaves a fingerprint. Webb reads those fingerprints with terrifying precision, and what it found made scientists pause. The case of WASP-39b. One of Webb's early targets was WASP-39b, a hot gas giant orbiting extremely close to its star. Temperatures exceed 900 degrees Celsius. According to older models, its atmosphere should be simple. Instead, Webb detected water vapor, carbon dioxide, carbon monoxide, and sulfur dioxide. Sulfur dioxide should not exist there. Its presence means active photochemistry powered by stellar radiation. This was the first direct evidence of complex chemical reactions in an exoplanet atmosphere. A bigger shock: carbon where it shouldn't be. On several planets, Webb found carbon-rich atmospheres that don't match their star's chemistry. That's a problem. Planets are supposed to inherit their chemistry from the disk they form in. Yet Webb saw planets that look chemically out of place. This suggests planets migrate far from where they form. Planet formation is chaotic, or our models are too simple. Super puffy atmospheres that should escape. Webb also observed small planets with atmospheres far too large to be stable. By all logic, stellar radiation should strip them away. Yet they persist, which implies strong magnetic fields, unknown atmospheric recycling, or missing physics. None of these are fully understood. Why this matters for life? Atmospheres are not decoration. They regulate temperature. They protect surfaces. They enable chemistry. If planets can maintain atmospheres in extreme environments, then habitable conditions may exist in places we never considered. The biosignature caution. Webb has detected methane, carbon dioxide, and water on multiple worlds. But scientists are careful. These are not proof of life, yet, because geology can mimic biology. Webb's real contribution is something deeper. It showed us how little we truly know about planetary atmospheres, and that ignorance is exactly where discovery begins. In the next part, James Webb goes even further, detecting chemistry that hints at environments where life could exist, and challenging the idea that Earth-like planets are the only ones worth searching. Are we looking for life in the wrong places? For decades, the search for life followed a simple rule: find planets like Earth. Same size, same temperature, same distance from their star. Scientists called it the Hycean zone. But James Webb Space Telescope is forcing a rethink, because some of the most interesting chemistry is showing up on worlds that look nothing like Earth. The old assumption. The traditional idea was clear: rocky planets only, thin atmospheres, liquid water on the surface, calm, sun-like stars. Anything else was considered hostile, uninhabitable. But Webb is showing us that nature doesn't follow our preferences. The rise of Hycean worlds. One of the most disruptive ideas to come from Webb data is the concept of Hycean planets. These are worlds that may be larger than Earth, covered by global oceans, wrapped in thick, hydrogen-rich atmospheres. Older telescopes would have ignored them. James Webb didn't. Why these worlds matter. Hydrogen atmospheres trap heat extremely well. That means a planet can stay warm even far from its star. Underneath that atmosphere, liquid water oceans could exist for billions of years. Webb has detected water vapor and methane in atmospheres consistent with this idea. Not proof of life, but proof of possibility. Life without sunlight. Another shock. Webb is studying worlds around red dwarf stars. These stars are smaller, cooler, and far more violent than the sun. They flare constantly. Old thinking said, life can't survive that. But Webb has detected atmospheres that persist despite intense radiation, which means magnetic fields may be stronger, atmospheric recycling may exist, life may be tougher than assumed. On Earth, life survives near volcanoes, in radioactive zones, at the bottom of dark oceans. Why not elsewhere? Biosignatures, a dangerous word. Webb has already detected molecules that, on Earth, are associated with life. But scientists are cautious because the universe can fake biology. Volcanoes can produce methane. Ultraviolet light can rearrange molecules. This is why Webb is not searching for a single molecule, but for patterns, chemical imbalances that should not exist together without constant replenishment. That's the real target. The big shift in thinking. James Webb hasn't found aliens. What it has done is more important. It has expanded the map of where life could exist. The search is no longer limited to Earth-like worlds. It includes ocean planets, ice-covered moons, thick atmosphere worlds, dark, energy-rich environments. Life may not be rare. We may have just been looking in the wrong places. In the final part, we'll ask the biggest question of all. What happens if James Webb doesn't just suggest life, but finds evidence that can't be explained away? What if Webb is right? The future of discovery. For now, the James Webb Space Telescope has done something extraordinary. It hasn't answered the biggest questions. It has made them unavoidable. When evidence stops being coincidence. Science doesn't change from one discovery. It changes when patterns emerge. James Webb is beginning to reveal patterns. Galaxies forming too fast, atmospheres too complex, chemistry too organized, worlds too resilient. Any one of these could be explained away. All of them together? That's when scientists pause, because the universe is behaving consistently, just not the way we expected. The next step, from possibility to proof. Webb is not a life detection machine. It was never meant to be. Its role is more subtle. It identifies targets, worlds where chemistry is active, atmospheres that shouldn't survive but do, places where future missions should look closer. The next generation of telescopes will build on Webb's map. They will search for chemical disequilibrium, seasonal atmospheric changes, planet-wide signatures of metabolism. This is how discovery happens, slowly, relentlessly. What happens if we find a true biosignature? Imagine this moment. A planet, dozens of light years away. Its atmosphere contains two gases that should destroy each other, but don't, because something keeps replenishing them. Not geology, not radiation, but biology. That discovery would not be loud. There would be no announcement at first, just quiet verification, months of cross-checking, years of debate, and then consensus. Life exists elsewhere. How that changes everything. Humanity has always asked the same question: are we alone? Webb is the first tool capable of moving that question from philosophy to physics, from speculation to data. If life is found, even microbial life, it means biology is not fragile. It means life is not rare. It means the universe has been alive far longer than humanity has existed. The most important discovery might be ourselves. There is another outcome. Webb may never find life. Not clearly, not conclusively. And even that would matter, because it would tell us how rare Earth truly is. Either answer is profound. Either answer changes how we see ourselves. Final thought. James Webb did not bring us answers. It brought us humility. It reminded us that the universe is larger, older, and stranger than our models suggest. Whether Webb finds life or only deeper mystery, one thing is certain: the universe is no longer silent. We are finally listening. End.